In the previous segment, we discussed about the wedges, and we saw how to evaluate the force which is required to push a wedge so that a mass of a certain mass, a block of certain mass can be lifted up. So that's what we did, and then we saw even the conditions of self-locking, so that if we remove the force, under what conditions the mass will not fall down by itself. So such things we discussed, and then we said that those are some way, in a way, a precursor to our study of screw threads. So now in this segment we will start the discussion of the screw thread, and for that let me draw a diagram like this. Say, suppose there is the head of the, then suppose I cut it from here. Sorry, should be in the same straight line. Yeah, maybe sorry, let me do like this. Okay, so here again something like that. Okay, now on this part I'll draw, though they are the same material, I'm just trying to drawing it by using a different color so that it will be clearer, nothing else. It doesn't mean that these are of different materials. And I shall erase these things in between here. Okay. Yep. So something like that, and then here I should, sorry. So now this I'll join like that, and here I'll join like this. So this is in a way a schematic of a screw thread. So here you are imagining that you are looking the thread from its side, and let me draw one more of these things so that okay, it will be like that. Yeah, it's okay. And so now, and then these are called, sorry, say from this distance to this distance, I'll name it as the lead of the screw. There are some subtle difference between the lead and the pitch, so that while discussing a problem maybe I'll come to that. But just for the time being, you just think that if I turn this screw thread, or if I move a single complete revolution on that thread, how far I'll move on the axis. So that's the lead, and then this angle, say this angle is alpha, and if you remember, this is like the angle the wedge used to make with the horizontal. So it's something like that. So if you can imagine that if you unwrap this, you will get a wedge like that. Okay, and then what else should I? Yeah, so that's more or less fine. And then one more dimension which is important, from the center of the axis to say the mid, so this distance of average radius, the mean radius is r. Okay. Yeah, so that means if you look it from, say, from this side, maybe if you view it from this side, it will look something like this. So I'll draw the, so this is the thread boundary and this is that shaft sort of, okay, and your mean radius is something up to this point. This is R. Okay. Yeah. So this is the view when we look from, say, this side. Yeah. And generally, how we use it is, a screw thread to lift up something. You might have seen in the screw jacks, which is generally used to lift a vehicle to in order to change the flat tire. So there, a schematic, if I want to draw, I'll just draw it like this. Maybe say a block sits like this on the ground. Okay, so something like that. Okay, and yeah, let's say here there is and this is ground. It is sitting on the ground. Okay, and then you have your say, sorry, the thread coming here. Sorry, it's something like that. It's coming inside this. Okay, something like that, and then I'll have my threads running here, maybe. Something like that, and here it's like that. The angles are not correct, maybe. So, yep. Okay. So, so the point is, if we try to turn this, this one, if we turn like that, then the whole thing will start, this screw thread will move up. Okay, let me, something like that, if I erase, so maybe it will be clearer. Okay, yeah, it doesn't matter, you understand what I'm trying to draw, basically. So something. Then what? Now, these are the basic things which we will require to explain things. Okay, so this is a thing which is connected to the ground. Okay, this is the jack maybe, and it's connected to the ground. If we now turn this, it will move up, and whatever load, suppose I show a load over here. Okay, say weight W. Let me bring it down, maybe. Let's see. Okay. So this way, sorry. So this W, this is the weight W, which we are lifting by this moment M. Say, if we are giving a moment M to this screw thread, so that it goes up, thereby lifting this weight W. Okay. So that means the equivalent thing I can show here. So this is W, and we are applying a moment across this, say M. Is that fine? Okay. Now, under such condition, we are about to evaluate that what should be the moment relationship between, I can also say in this way, that what is the relationship between this W and this M and the geometrical parameters of the screw thread. So this is the whole thing which we are going to discuss now. Okay. So yeah, coming to the concepts of wedges now, let's see if this is sort of angle alpha. If I draw the perpendicular to that surface, this slanting edge of the screw thread, I have drawn a perpendicular there, and this is the vertical, that is through the axis of the screw thread. So that means this angle also is alpha, right? And now imagine that our reaction from, just consider a small segment over here, okay, a small segment maybe here. On that small segment, the reaction that is coming from this block, that is from the ground, you can say, which is coming, and then we are assuming that it is now just on the verge of slippage. So it is just about to move this weight W. Okay. Under that condition, what will happen? This angle will be your phi, isn't it? The angle of repose, right? Now, if that is phi and this is alpha, so now we are in a condition to correlate these things. Think about if this is the small elemental force R, its horizontal component. Let me show this R over here. Say this I have chosen maybe at this location, say this is a segment which I have chosen, maybe a small segment, and the R is from downward, it is showing up, and I'll show here the vertical, the horizontal component which is acting in this direction, which is tangential to this circle at a radius R. So maybe, so I'll show this in purple color. So this is, which is the, I'll say R sine of alpha plus phi, okay, and the vertical component will be actually balancing W. So let's write down the equations of equilibrium. Under what sort of forces which parts are in equilibrium. Now this moment is basically being equal to all the summation of these forces throughout this over all the small segments. If we sum them up, so I'll say that, okay, this sine of alpha plus phi is constant for all those little segments, and say summation of R, I'll say, of all those small pieces. Now that's one relation which relates the moment. I think I'm missing something, right? Because I'm taking the moment and this is just the force times R, the small r. So I will put a small r over here, right? So m times m is equal to, this is the force and this is the moment arm. So r times small r times sine of alpha plus phi times capital R, and that you sum up to get the total moment. And what about the W? The W will be it's like, you know, cos of alpha plus phi and summation of R. Fine. So that is it. So then we'll just eliminate this summation of R, the reaction force. If we eliminate, we will get a relationship between them, okay, and that relationship will be we shall get, what shall we get, M is equal to W times R times tan of alpha plus phi. Okay. So just divide them basically. Okay, this to this, if you divide, you will get M over WR tan alpha plus phi, and then so okay. So this is the relationship which I was talking about, that the relationship between the weight which you want to lift and the moment that you want to apply or you need to apply. Okay. And then the geometric parameters are the small r, the mean radius of the screw thread, alpha, the thread angle or the wedge angle, if you think, if it helps, and phi is your angle of friction. Okay. So that's how you relate. But now there is another way to completely interpret these results, and that will be by creating the wedge, which let me go to that slide itself, and from here you just try to imagine that you have unwrapped. So, when I say that, something I think I can write here also to evaluate alpha. How do you evaluate alpha? For that, I'll do it here. So you see here, when you unwrap it, you will get, shall I draw it here? Okay, you are just unwrapping it, and this one is 2 pi times r, and this height is L. Okay, so this is L, this is 2 pi r, so tan of alpha is equal to L over 2 pi times r. So that is how you should in fact calculate alpha from the geometry of the screw thread, using the mean radius of the screw thread and the lead of the screw thread. And then yeah, it's done. So you know the coefficient of friction from which you can calculate phi, you know the mean radius. So to lift a particular weight W, you can calculate now how much moment you need to apply to the screw thread. Now yeah, I was talking about another viewpoint of calculating this same equations is by drawing the one which I drew just a few minutes back, this the unwrapped segment. Okay, so the unwrapped segment, if you are seeing like this, this is a single revolution of the thread we have now unwrapped, and the force now you can think that you are applying a force P which is nothing but M over R, which is equivalent to this. Okay, means applying a torque of M is like applying a push of M over R, right? Now and here we can now see that, say this is a perpendicular to the surface, sorry, so this is perpendicular to the surface and on both the directions maybe, and this is the vertical, that is through the axis of the screw thread. okay. And now the weight is actually acting on this way, okay. So this is the weight, and the reaction force is coming somewhere from this direction, right. So this is R, and now suppose this is what, this is alpha, because this angle is alpha. So yeah, I'll show that here in a moment. And this being phi, right, because things are on the verge of just slippage, so this angle will be phi. You remember we were telling that the total reaction will move angularly like that, and just stay at that location on the verge of slipping. And yeah, I was trying to say that, right, that this angle, so this height is, you know, L, and this length is 2 pi r. So tan of alpha, because this angle is alpha, is equal to L over 2 pi r. Okay. Now, so from here you can again write the balance equation, that R of, so now you don't have to think about the moment and all those things. So this is the complete reaction which is coming. So R sine of R, this is sine of alpha plus phi, is equal to this m over r, and r of cosine of alpha plus phi, sorry, so this looks like a t to me, alpha plus phi is equal to w. Okay, so the force balance in two direction, x and y, so that straight away gives us again the same relationship, that is m is equal to w r tangent of alpha plus phi, right. So this is another way to, whatever is comfortable to you, you think in that term. In fact, I would suggest that you should be comfortable with both the viewpoints. Okay. Now, if this is the case, this is the way to look at this situation. So the advantage I'm just going to tell, that you can now very easily think about that. If you now suppose the screw thread is self locked, okay, in this case the locking condition will come that from the fact that alpha will be equal to phi. So to see that, it's very easy here, you see. I'll draw this picture once more here. Say, suppose this is your unwrapped thread, okay, this should have been vertical, okay, unwrapped thread, and if it is self locked, then you will have to apply a pulling force now to bring it down, right. So I'll draw the pulling force in this direction, which again will be equal to, say, m over r. And if I draw, say, the vertical line through this and the vertical to the ground, so this is alpha, and your weight is coming from this direction, okay, this is w, and suppose your angle alpha, sorry, phi is greater than alpha, so I am drawing for that condition, which will look something, say, like this. Now you have to, in this direction it should come, isn't it? Sorry, because you have to have R to be in balance, see, and this angle must be, you know, phi, and we have assumed that phi is greater than alpha. This is the case, because and then now I was talking about, what is the condition of self locking in this condition, this in the case of screw threads. See this, when this phi becomes alpha, let me draw the alpha again here also. So this also is alpha, this phi. Now if R, that means we are saying that under its own weight it is falling down, that means this force is not there. So it will be a two force members and it is just on the verge of slipping. Then this R will be along this line. So that means phi is equal to alpha. So under the screw thread condition, when phi becomes alpha, it is on the verge of slipping. So when phi is greater than alpha, you have to apply a load in this direction to unwrap or unwind the screw thread. Okay, and just to show the another case where phi is less than alpha. So that means alpha is more, that means it will tend to fall down under its own weight. So that means you will have to apply a force in order to keep it in that position. So and then how to find out that? Let me draw another picture. So like that here. So now alpha is very high, so that alpha is more than phi. Okay. So in this case, your phi is less than alpha. Alpha is too high, and then under these conditions, what will happen is, let me again draw the perpendiculars, usually the usual way. So this is like that, and this angle is alpha. And now again your force you have to apply in this direction so that it will not fall by its own weight or under the weight of this W. So P again is equal to M over R, and again I will show the weight like this. Okay, and now you have to apply your R in this direction. Say now your alpha is more, so this is alpha, so I'll say R something like this, right? So this is alpha, this is phi, and it is again on the verge of slippage, but you are applying this force in order to keep it balanced. Otherwise, if you remove this force, which is actually keeping it intact, the thing will fall under this weight W, because phi is equal to alpha is the condition of self locking under this case. Slightly you increase alpha, it will fall down. Slightly you decrease alpha then phi, it will be just under locking, and the phi is equal to alpha is the case of just on the verge of slippage, because this picture will tell you that if when this phi is exactly at alpha, these two are in the same direction, equal and opposite forces will balance, collinear, and this force you won't require, and that means this is 0, this is the two force member, and it is just about to slip under its own weight or the weight W. So this interpretation gives a lot of very easily understandable ideas of self locking, the force which is required for unwinding the screw, or the force which is required to stop from the screw to fall down when that condition is prevailing, that is alpha is more than phi, and the normal way, the lifting moment or the lifting force which you require. So all these things can be seen from this picture. So both this interpretation, this plus this, I would say are very important to understand and to visualize any problem to be solved or tackled under these type of screw thread problems. Okay. So fine, so we will stop it here and we will see some problems, and then it will be much clearer. And in the next segment we will see about, as I had promised, the pulley and belt drive concepts. Okay, see you next time.